The last session we've been talking about finite fields, the number of elements that can happen in a finite field, and we found that we cannot create a finite field of any number of elements. It has to be in the form of p to the power of n for some prime p and n greater than 0. And we have an example of 4 elements. We already established this one in the earlier session, and also we took this example to show that p square, 2 square elements can be formed. A field of 2 square elements, 4 elements. And that was actually 0, 1, alpha, 1 plus alpha, where alpha is a 0 of x square plus x plus 1 in z2 x. And this is an irreducible polynomial, and we found that basically these 4 elements are the zeros of x to the power of 4 minus x. There are 4 different zeros of this element, this polynomial. Now, there are 2 things what we need to observe here. One is this, let us say, z2 star. Actually, this is an extension of z2. One thing what I want to observe here is that if you take z2 star prime is prime star this is actually the multiplicative group of non-zero elements from here. That is 1 alpha 1 plus alpha. Now what is alpha square? Alpha square is actually 1 plus alpha, because alpha is a root of this. So alpha square plus x plus 1 is equal to 0. So alpha square is equal to minus alpha minus 1. But minus 1s are always 1s in C2. So 1 plus alpha. And what is alpha? Okay. So we can write this as, what is alpha cube? Well, that is alpha times 1 plus alpha. That is alpha plus alpha square is equal to minus 1 is equal to 1. So we can write this as alpha square alpha cube. In other words, this is a cyclic group generated by alpha. So you can write it as a cyclic group generated by alpha. The reason for that is we have a result in the elementary field theory. That result is this. I'm not going to prove this, but the result is, let F be a field and F star, comma, multiplicative multiplication binary operation of field is a cyclic group. Let's take another example, C5. C5 is 0, 1, 2, 3, 4, and C5 star, Z5 is a field, is equal to 1, 2, 3, 4. Now you take 2. 2 is equal to 2 to the power of 1. 2 square is equal to 4. 2 cube is equal to 3. 2 to the power of 4 is equal to 1. So it is actually generated by 2. So that's what this says. The multiplicative group with the elements, non-zero elements from Z2 is a cyclic group generated by some element. So what does that mean? That means let E be a finite extension of a finite field finite field F. Then E is a simple extension. The reason is E star with the multiplication is a cyclic group. When I say E star, it is actually non-zero elements of E. With multiplication is a cyclic group. That means there exists an alpha belongs to E star such that E star equal to generated by alpha. So every element of E star is is generated by alpha. So that means E is equal to f of alpha, because it is the whole thing is generated by this. So this actually we should be very careful. It is a finite extension of a finite field. We know that there are finite extensions of Q. For example, Q root 2 comma cube root of 2. This is a finite extension of Q, but Q itself is not finite, and that is why this is not simple. There are two generators here. Another thing I want to notice here is, see here, you mentioned as C2 star is equal to 0, 1 alpha, sorry, 0, it's not 0, 1 alpha, 1 plus alpha. And that is also again equal to 1 or alpha, alpha square, alpha cube. Or you can say 1 alpha, alpha square. Let us take the third representation, not this, because we need a 1 already there. So leave it as 1 alpha square. And this is a simple extension of, so Z2 prime. Z2 prime is equal to Z2 of alpha. That's what I'm trying to say here. But see, what is actually Z2 of alpha? Z2 of alpha is a 0 of x square plus x plus 1. So it has to be like this. A0 or A plus B alpha, where A comma B belongs to Z2. This is the definition of the simple extension here. Because it contains all the polynomials in alpha whose degree is strictly less than the degree of this, and that is this. And that is what this one is. That is actually alpha 1 plus alpha. But this also can be considered as a cyclic group. Okay, over here there is a 0 also here, because I am not taking the multiplicatives. So these are the elements. But when you take this one, star of star of alpha, that contains only one alpha square, and that is precisely 1 alpha 1 plus alpha. So don't get confused. These two are same. These two are same because of this relation. So both are same. So the result is, if E be a finite extension of a finite field, then E is a simple extension. That is the result which we are going to use. What we found is that every finite field has p to the power of n elements for some prime p and integer n greater than 0. We already established this one. Now our question is, for any p, any prime p and integer n greater than 0, can we have a field of p to the power of n? We know that every finite field has got p to the power of n elements, but that does not mean that if you take any prime and any n greater than 0, we can definitely create a field of p. Do that kind of fields exist? That is a question. So let us see whether we can do it or not. So the way we are going to approach this problem is, let ZP bar be the algebraic closure of ZP. When I say algebraic closure, we have a result that every field has an algebraic closure that is, every field F has an algebraic closure that is algebraically closed. We know this result. Closed. And it is denoted by always F bar. Meaning this closure of F is algebraically closed. Meaning every polynomial in here has a 0 in here. So like that, ZP has an algebraic closure. So that means ZP bar is algebraically closed. Meaning every polynomial in here in ZP has a 0 in here. So consider this polynomial x to the power of p to the power of n minus x belongs to ZP of x. Has zeros, has all zeros in ZP bar, because ZP bar is algebraically closed. Now we need to show that all these zeros are distinct. Another thing is, we need to prove that the collection of all zeros of x to the power of p to the power of n minus x minus x is a field. So these are the two things we need to prove. This is already assumed. ZP is algebraic closure, and x to the power of p to the power of n is a polynomial here, and all zeros are in CP bar, the closure of this, because it is algebraically closed. Now we have to show that all the zeros are distinct. And if you take the collection of all the zeros, that forms a field. Then that field has p to the power of n elements. Why? Because this polynomial has got at most p to the power of n elements, but all the zeros are distinct, so it will have the p to the power of n elements. So let us prove the first one. All the zeros are distinct. So let x to the power of p to the power of n minus x belongs to ZP bar. Sorry, ZP of x. And alpha b a 0 no, let us not take that way. So this can be written as x to the power of p to the power of n minus x is equal to x times x to the power of p to the power of n minus 1 minus 1. So 0 is a 0 of x to the power of p to the power of n minus x. Now we are going to take only this. So let alpha be a 0 of x to the power of p to the power of n minus 1 minus 1. So let us divide this. When you divide, so that implies x minus alpha is a factor of x to the power of p to the power of n minus 1 minus 1, because alpha is a 0. So x to the power of p to the power of n minus 1 is equal to x minus alpha times a g of x, where g of x is equal to, using the long division, I'm not going to do it here, you can do a long division here, it will be x to the power of p to the power of n minus 2 plus alpha times x to the power of p n minus 2 n minus 3 plus alpha square times x to the power of p to the power of n minus 4 etc. last will be alpha to the power of p to the power of n minus 2. There are x to the power of pn minus 1 elements. See, if you, for just an example, you say x cube minus 1 divided by x minus alpha. So this will be plus 0 x square plus 0 x minus 1. So this is x square. So x square x cube minus alpha x square. So plus alpha x. So alpha x here. So this will be alpha x square plus 0 x. So this will be alpha x square minus alpha square x. So alpha square x minus 1, that will be plus alpha square. That's exactly what I'm saying here. This is actually our x2. So there are actually 3 elements. 1, 2, 3 elements, and we have x to the power of n minus 1. This is our 3. There are 3 elements. Okay. So let us take this as p of x, or let us take it as f of x. So f of alpha, then what we do is g of x is this. So let's take g of alpha. G of alpha is actually alpha to the power of p n minus 2 plus another alpha to the power of p n minus 2, because alpha times this, plus dash 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 alpha to the power of p n minus 2. How many times? We have p to the power of n minus 1 times alpha to the power of p n minus 2. But what is alpha? Alpha is actually alpha to the power of Pn minus 1 is equal to 0, because alpha is just alpha is a 0 of that polynomial, right? So let us write it here. So and alpha to the power of P to the power of n minus 1 is equal to 1. And that means alpha to the power of P to the power of n minus 2 is equal to 1 by alpha. This is possible because alpha is coming from a field. So this will become P to the power of n minus 1. Sorry, this is actually P to the power of n minus 1 minus 1. P to the power of n minus 1 times alpha to the power of P to the power of n minus 2. That is actually 1 by alpha. This cannot be 0. Well, let us expand this one more step. See, P, this is an element from 1 by alpha is an element from Z2 prime. Alpha belongs to ZP closure. So this is actually of characteristic P. So when you multiply this one will become 0. So it will be, that implies P to the power of n minus 1 of 1 by alpha is equal to minus 1 by alpha. Cannot be 0 because alpha is different from 0. Because we already took 0 here. So this cannot be, alpha cannot be 0. So what does that mean? G alpha is not 0. Implies alpha is not a 0 of G of alpha. So once you have assumed that alpha is a 0 of this, then that alpha cannot be a 0 of any factor of Z P to the power of n minus 1 minus 1. And that is what we want to prove here. All these zeros are distinct. So that implies all zeros of x to the power of P to the power of n minus 1 or x to the power, let us write minus x, are distinct. Now next thing what we need to prove is the collection of all zeros of x to the power of P to the power of n minus x is a field. So let K be the collection of all zeros of x to the power of P to the power of n minus x that belongs to Zp of x. Definitely 0 and 1 belongs to K, because if you put 0 here, it is 0, because 0 and 1s are always zeros of this. Okay. Now let alpha beta belongs to K. That means alpha and beta are zeros of this polynomial. And what does that mean? That means alpha to the power of p to the power of n is equal to alpha, beta to the power of p to the power of n is equal to beta. Now let us see what is the condition that an element to be a zero of this. If you take gamma, if you want to prove gamma is a zero of this or gamma is an element of here, we need to prove that gamma to the power of p to the power of n is equal to gamma. If this condition is satisfied, gamma belongs to K. Our object now here is to show that K is a field. Already we have zeros and ones. We need to prove that alpha plus beta belongs to K, alpha beta belongs to K, the inverse, additive inverse of this belongs to K, and multiplicative inverse belongs to K. Then we are done. So let us see alpha plus beta to the power of p to the power of n is equal to binomial theorem expansion. So alpha to the power of p to the power of n plus p to the power of n, alpha to the power of p to the power of n minus 1 beta plus dash 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 plus beta to the power of p to the power of n. See, these are all coming from ZP bar, closure of CP. So this is actually a field of characteristics P. Meaning all these intermediate elements are zeros because this is a power of P. So and it's coming from, these are all coming from elements from a field of characteristics P. So this is basically equal to alpha to the power of p to the power of n plus beta to the power of p to the power of n. And what is alpha to the power of p to the power of n? That is actually alpha and this is beta. So that means alpha plus beta belongs to. Then now alpha beta to the power of p to the power of n is equal to alpha to the power of p to the power of n times beta to the power of p to the power of n. That is alpha beta implies alpha beta belongs to K. Now minus alpha to the power of p to the power of n is equal to minus 1 p to the power of n times alpha to the power of p to the power of n. That is equal to minus 1 p to the power of n times alpha. Now, this is equal to minus of alpha because minus 1 whole to the power of p to the power of n is equal to minus 1 for all p greater than 2 because this is a odd number, so this will become minus 1. And when it is 2, minus 1 to the power of 2 something, that is actually plus 1. So that actually is equal to minus 1 in Z2. So in either way, minus 1 to the power of p to the power of n is always minus 1. And that implies alpha belongs to, minus alpha belongs to K. Now we have one more thing to prove. 1 by alpha to the power of p to the power of n is equal to what? 1 by alpha to the power of p to the power of n, and that is equal to 1 by alpha, and that implies 1 by alpha belongs to K. And that shows that K is a field. So K is a field containing all the zeros of x to the power of p to the power of n minus x and all the zeros of x to the power of minus p to the power of n minus x are distinct. That means K is the field which we are looking for. So K is a field that has p to the power of n elements. So for every prime p and in an integer n greater than 0, we can find a field of order p to the power of n. So what we have done is for every prime number p and integer n greater than 0, we can create, or you can say a field exists with the p to the power of n elements. That field is called the Galois field of p to the power of n and is denoted by GF p to the power of. So what are the properties of this? G to the power GF of p to the power of n is equal to alpha belongs to CP closure such that alpha is a 0 of x to the power of p to the power of n minus x that belongs to Cp of x. So we know exactly the elements of this field.